Okay, good afternoon, everyone, again. So this week we have Mehmet Kerim Yucel with us. Mehmet Kerim Yucel received his bachelor degree from electrical engineering from Bilkent University in 2011, and he holds a Master of Science and Master of Philosophy degrees from Brunel University. He was a research engineer at Huawei European Research Center MIS previously, and he is now a senior researcher at Samsung Research and Development Institute in London. He is also pursuing his PhD studies at Hacettepe University in collaboration with Pınar Hoca, Pınar Duygulu, and Gökberk Hoca. His PhD studies focus on adversarial machine learning and weakly supervised learning. Thank you, Kerim, for being with us, and the screen is yours.
Thank you for having me. First of all, I feel really proud and happy to be here. So today I'm going to talk about a recent paper that we published in WACV 2021, published I think last month. And the paper is called Red Carpet to Fight Club, Partially Supervised Domain Transfer for Face Recognition in Violent Videos. It is a collaboration between myself and Yunuscan Bilge, Nazlı Çizer Cimbiş and Pınar Duygulu from Hacettepe University, and Gökberk Cimbiş from Middle East Technical University. So before I start talking in depth about the paper itself, I would like to take a step back and focus on faces and computer vision. So faces are, as we all know, are an integral part in computer vision. So when we talk about faces, we can effectively focus on various tasks such as face detection, facial landmark detection, face alignment, frontalization, face super resolution, restoration, and metric learning and representation learning for face recognition, and many others that we can name. But we are going to focus on face recognition in this presentation. And when we talk about face recognition, two tasks come to mind in general. That is identification and verification. So just as a quick background information on what these tasks are. So when we talk about face verification, roughly in a glance, the task is to, we assume that we have two images and we want to find out if the persons in the images are the same or not. But when we talk about face identification, it is quite analogous to image classification. We have an image and we want to find out who is that person in the image. And this talk will primarily focus on face identification, but not in a conventional face recognition / identification manner, but in a more specialized, hopefully a more realistic scenario. So in that slide, you can see several axes that I have prepared. And this is a rough and arguably in-depth visualization of how face recognition research is taking place. So each arrow, each dimension represents a potential dimension of face recognition research direction, let's say. And I will briefly mention them before I go into detail about the paper. So first of all, when we talk about face recognition, in the previous years, what we need to focus on is the scale. So what scale means is that maybe a few decades ago, when we trained our models or when we extracted features and tried to find and recognize the faces, we had really limited data sets. But as the years passed by, especially with the recent rise of machine learning and deep learning, we started seeing publicly available data sets such as MegaFace, VGGFace2, and WildestFaces that are in the order of million images. And even more in tech giants like Google and Facebook, they have even larger data sets that are not released to the public. So scale is the one dimension that we mentioned. And the other one is the class imbalance. So when we talk about class imbalances, in face recognition, we can have a closed set face recognition scheme or an open set regime, let's say. And the third dimension is the detrimental effects that the images may go through, such as occlusion, various levels of blur, variance in ages for the same person, and different scales and different poses. The fourth one is whether we are talking about face recognition in still images or in videos, basically. And that is, all of these will be quite relevant to what we're doing in our paper. The fifth one that I want to mention is the cross-domain face recognition. So as the name implies, we can train our model on in one domain of images, and we would like to, we may want to recognize the same people in another domain. So that can be a thermal to electro-optical domain shift, or synthetic to real, and effectively any other different domain, pairs of domains that you can think of. The last one, and if not the most important one, is face recognition in what I call tailored scenarios. So we can try to recognize faces, like masked faces, especially in the last year that became quite prominent. And we can also try to recognize faces in any other disguised setting. We may want to recognize faces in low light, and we may want to recognize faces and effectively go further and recognize the ethnicity, age, and gender of the person. So keeping all of these in mind, when we started working on that paper, we thought of a realistic scenario, and we basically tried to list the characteristics of a potential realistic scenario that we want to mimic. So the first one is the data discrepancy between training and deployment data. So it is effectively a domain shift. So we are going to have access to data in domain A, but we're going to want to have the ability to recognize the same faces in domain B. And that can be, this domain shift can happen because of the nature of the two domains, or it can happen through time. The second thing is the lack of samples for some of the classes in our test set, let's say. And here we want to mimic the extreme class imbalance setting, where basically in some of our test classes, we're not going to have access to any images during training. And on top of that, the third factor that we want to mimic is the limited training data. So we are going to have low per class sample count, because in our realistic scenario, we are actually basing it on a surveillance-like scenario, and we're going to have, we may potentially have copyright issues, privacy issues. So the idea is that we have to work under a low data regime. And the fourth one is we would like to have the ability to use still images as well as videos equally efficiently. So keeping all of these in mind, it is somewhat clear that we need a new problem formulation. And again, looking back to these 4 factors that I listed, it is going to be at the intersection of domain adaptation and zero-shot learning. So enter partially supervised domain transfer. So this is our new problem formulation is what we call partially supervised domain transfer problem, which I will go into more detail in the following slides. But what I want to do first is go back to the dimensions that I have shown in the previous slide and make sure that we note characteristics in each dimension. So when we talk about scale in our partially supervised domain transfer problem, we are going to have limited data. So we're not going to have access to millions of data for n number of people. So our per class sample count is going to be limited. The second thing is the class imbalance dimension. And as I mentioned earlier, we're going to have unseen classes. So what that means is we're going to train on n number of people, let's say, and we would like to recognize the people that we have not trained for. The third dimension is the detrimental effects. So because it's realistic, we wanted to mimic basically all naturally occurring effects such as occlusion, blur, age, scale, and pose. And what is different in our case compared to the other face recognition benchmarks and problems is that we are not really restricting any of these at all. So it is, as the name implies, it is completely in the wildest scenario. So our problem formulation inherently has that, and our proposed solutions need to handle that implicitly. The fourth dimension was the set-based dimension. And in our problem, we're going to work with images and videos alike. So going into more detail about our specific scenario, we are going to have cross-domain elements. We're going to work with what we call violent videos, fight videos, and we're also going to work with clean passport-like images. And lastly, and potentially the most important one, is our Z-tailored scenario, which focuses on fight scenes. So again, just to better visualize what I've said and to wrap it up, partially supervised domain transfer keeps in mind 4 different factors that we listed to mimic, that we believe are required to mimic a realistic scenario. So we talked about data discrepancy. We realized that data discrepancy by having fight videos and clean photos in training and in deployment and training data respectively. So lack of samples is realized by not having violent videos of some subjects. Limited training data is realized by having a small data set, basically. And as I've mentioned, we are going to exploit both image sets and still images. And to wrap up, our new problem formulation combines domain adaptation and zero-shot learning. So what is partially supervised domain transfer, and what is the plain words definition of it? So the goal of partially supervised domain transfer is to transfer a model trained on clean images to the domain of violent videos. And while doing so, the training videos are going to be available for only a subset of subjects. So what that means is, on the left-hand side, you can see still images of some actors. And we're going to train a model, we're going to train a classifier, to be specific, on these actors. And we will make sure that this classifier is going to work well with the violent videos you can see on the right. So obviously, we need a benchmark data set to do that. And towards this end, we collected and released what we call it the WildestFaces data set. So to create the data set, we collected violent movie scenes from YouTube. That consists of car chases, fist fights, gunfights, heated arguments, and so on. And in general, it has 64 actors over 2K videos, and in total, it makes up around maybe 64 keyframes. And we annotate the face regions and then crop them to create our data set. So that part is basically the violent video domain. So we have data in domain A, let's say, and obviously we need data in domain B too. So to create the domain B data set, we basically take the IMDb wiki data set and we complement it with missing actors. So, and what we end up with is we have passport-like clean images with minimal changes in facial directions, the same number of actors, and roughly 8K frames. To talk more about the characteristics of the data set, as I tried to mention before, we are not limiting any of the detrimental effects that we have mentioned. So we have various blur, scale, pose, age profiles across the board. And as you can see, we have medium, high, and severe blur, basically making up the huge part of the data set. And we have various scales and an arguably uniform distribution of different postcodes in our data. Another important characteristics of our data set is that for 64 actors, we have an average age variation of 13 years. So the problem is not to basically have a good identity representation, but to make sure that we handle the age variation for an actor as well. And obviously, we have what we call significant occlusion in basically half of our available data. So having talked about the data set and the problem briefly, I would like to talk about the evaluation setup and how we divide our data and how we train, validate, and test it. And I think that's important to mention at this point, because what we're doing is not really similar to the conventional face recognition evaluation protocols. And it is good practice to mention that here. And I think it's going to give a better idea of the problem definition at hand. So for our data sets, we borrow from generalized zero-shot learning principles. And in our training, we train our classifier with clean images of all the actors. And then we perform the rest with the videos of 40 scene classes. And I'm going into more details in that part, but we use the clean images to train a fixed classifier, and then we train with the violent videos of 40 actors to make sure that we have a good feature transformation. But I will go into more detail in the following slides. So for validation, we're going to validate completely on the violent video domain, but in addition to the 40 scene classes in the violent videos, we're going to validate on 10 additional unseen classes. And during the test, quite similar to a generalized zero-shot learning evaluation, we're going to test on all of the videos of all the actors. To wrap up on the data set, so during collection of the data set, we made sure that obviously the data set itself is representative of the problem at hand. So similar to the zero-shot and generalized zero-shot learning data sets, unseen classes in validation and test sets are picked from the classes that have least amount of samples. And secondly, and more importantly, when dividing the training class samples into the splits for train, validation, and test, we took into account the age, pose, and blur variances. So what that means is on the right-hand side, you can see, let's take the first row, and you can see Sean Connery. And on top left, in the training, we have an image or a video of Sean Connery in his early stages of his career. So he's fairly young. But as we go to validation and test, we see the difference. So he's getting older. So this basically adds another layer of complexity in our data. And effectively, it forces to learn a future transformation that is age invariant in a way. And in the other rows, you can see maybe not age, but other effects in action. So in the third row, you can see different poses. In the second row, you can see different levels of blur and occlusion. So we make sure that these effects are taken into account. And lastly, about the data set, even though we're talking exclusively about face recognition, we actually annotated our data sets for face detection as well, and then created the face recognition samples. So, and these are available publicly too. So going into the actual part of defining our problem. So partially supervised domain transfer problem, that's what we've been talking about. So it is about training a classifier in the source domain. And what we mean by that is we take the clean passport-like still images and we simply train a classifier, right? It's a simple classification task. And we do so with a fixed image representation. And I would like to highlight that because we're not performing any feature or representation learning throughout our study. What we only perform is that we effectively learn feature transformations. So the representations are extracted from fixed networks. So we trained a source domain classifier, which has a really good accuracy, let's say. But what we want to do is we want to make sure that this classifier will work well with the features or with the representations of the target domain. So we take the classifier that we trained and we plug it in, And now the target domain is going to provide us. So we're going to have maybe training or testing videos in violent videos. And what we need to have is we're going to have some representations coming from these videos, but we want to make sure that we transform these features in a way that they're going to work well with the source domain classifier. And I will go into more detail in these parts. So, but before I go into more detail, so this partially supervised domain transfer problem, we divided into two parts and we tackle them individually and then combine them. And the first part is what we call the classifier transfer. And the second part is what we call the temporal adaptation. So the first part is, as I mentioned, classifier transfer. So to define classifier transfer, it is basically adapting a classifier pre-trained in the source domain, in our case, the red carpet domain, the clean still images domain. And so taking that classifier and adapting it to the target domain representations. And target domain representations are coming from the violent movie videos. And while doing that, we are only using the training classes. So it is effectively a subset of all the classes available in the network. In plain words, what we are trying to do is transforming target domain representations, which are violent video movies, such that they will work better with the source domain classifier. So effectively, it's a simple feature transformation problem. And obviously, to solve that, we consider several alternatives. And we start from potentially simplest alternative, which is a simple, fully connected layer. And as we populate our benchmark, our baseline methods, we include more complex domain adaptation methods like MMD, maximum mean discrepancy, and ADA, adversarial discriminative domain adaptation. So these are well-known unsupervised and supervised domain adaptation methods that basically have state-of-the-art results. But obviously, there are problems that we encounter, and what we see is all the alternatives that I mentioned are rather complex. So I think it's natural to ask how complex can a simple, fully connected layer be? But in our case, it is. And that's because we have a combination of limited training data, and even though it's not complex, we have large number of parameters. And maybe in a fully supervised setting, that is not going to be a huge problem, but because we are evaluating and we're basically operating in a zero-shot learning setting, this is a recipe for overfitting to seen classes. So we're going to recognize seen classes significantly better than unseen classes, and that is going to lead to poor results. And so having seen that, we obviously need an even low complexity alternative. So even if a simple fully connected layer is too complex for our problem, we need to go even less complex. And we make an assumption here, and we assume source and target domain representations are sufficiently correlated. And what I mean by that is, obviously they're different, but they are of the same person, and there should be a correlation between these two, because we know that there's a correlation, but we need to learn a transformation that is going to basically realize that and capture that correlation, but even in a low complexity regime. Towards that, we propose what we call an affine-transform layer, and it does what its name implies. It simply learns an affine transformation. And we move on to extending it to what we call a residual stacked affine layer. It is simply a stacked version of multiple affine layers with skip connections that we are going to talk more about in detail. So we know what classifier transfer is now, and we talked about alternatives, and we talked about what we proposed. What we need to tackle is the temporal adaptation aspect. So our problem, as we have mentioned before, it has videos, violent videos, and also still images. So we need to obtain a video representation vector suitable for our task. And in plain words, we need to find a way to aggregate images and features to a single fixed size vector. And towards that end, again, we start from the simplest alternatives, like simple majority voting over individual predictions, average and max pooling over the features of individual images. And lastly, we go into more complex regimes like aggregation networks operating over images and the widely popular self-attention mechanism to make sure that we implicitly have a, and we basically tackle temporal adaptation aspect. But again, there are other problems that we come across, and that is potentially, apart from self-attention or some of the aggregation networks that we mentioned, the other alternatives don't take into account the fact that not all frames are created equal. So let's say in a video, in a fixed video, we're going to have changes in pose, occlusion, blur, and that is going to detrimentally affect our overall accuracy. And basically, treating every frame with equal importance does not work. So what we need to do is that we need to handle the multimodality and the noise in the face tracks in videos that we have. And in plain words, we need to learn to use or weight the important frames in a given video sequence. And what that means from a more abstract perspective is that we need to exploit the latent information available in our videos. So that can mean that we're going to learn to focus on informative poses, or we're going to focus on we're going to attend to images that have less blur, right? And towards that end, we propose what we call an attentive temporal pooling mechanism. It is a simple softmax-based attention mechanism that we go into more detail in the paper. So going into, just to give you an overall summary of what we talked about. So in that diagram, you can see on the right-hand side, we have our image data consisted of still images of clean, still clean images of the actors that we mentioned. And what we do, we simply train a linear image classifier. And as noted here, it's going to be fixed. So we take that, we freeze it, and then what we have is we're getting video face tracks. And obviously they're represented as a sequence of video features. And what we want to do is the temporal adaptation part. What we do is that with the attentive temporal pooling mechanism, we learn to aggregate these features and come up with a single image, single fixed vector of feature vector. So we had video features, and now we have a fixed feature. So we learned how to temporally adapt and aggregate. Now what we need to do is basically handle the domain adaptation part of the problem. So we have the aggregated features, and through what we call the residual stack define transform, we realize that transformation. So actually the whole point of the paper, the partially supervised domain transfer problem, is the bottom part of the paper. So bottom part of the diagram that you see. The fixed classifier is just trained once, and we want to optimize the performance of incoming video features in when subjected to that classifier. So now that we know the problem definition and what our proposed approach is, we start our ablation study. So to begin with, in the classifier transfer part, we talked about affine layers and how they are better than how they're potentially better than the other alternatives that we mentioned. And in this plot, you can see that that in real life, basically. So on the left-hand side, we have the random guess. Obviously, it's going to be quite bad. And what's interesting is the no transfer case. So we're effectively doing no classifier transfer, no explicit handling of the domain adaptation aspect, and it still works well, right? So it is significantly better than the random guess. So we can say that is a good, strong baseline. But the problem is when we try to do any kind of classifier transfer with the fully connected layers or other alternatives that we mentioned, they do not work. They're actually far worse than not doing it at all. And we briefly mentioned that because of the limited training data and high parameter count. And you can also see that state-of-the-art models like MMDFC. And I noted it with MMDFC because that's the original implementation, but we are going to talk about the alternatives as well. But basically, long story short, MMDFC, AdaFC, and FC, they don't work. They're actually worse off than not doing classified transfer at all. But a single affine layer, with, as you may guess, with a fraction of the complexity of compared to the alternatives, outperforms all, and it actually improves on the no transfer case. So it does make sense to do it. And lastly, I want to mention affine layers improves existing methods as well. So you can see that MMDA is better than MMDFC, maybe still not better than the no transfer case, but it is better. And you can see EDA-A actually outperforming no transfer case, but we couldn't even put EDA-FC, its original version, because it failed to converge. So we know that affine layers work. And the question that we need to answer with our ablation study is how many affine layers would be the ideal setting. So basically trying to push the boundaries to have even better accuracy. And clearly, what is the best temporal pooling mechanism? And what you can see in the slides is a limited subset of the temporal adaptation methods that we're testing. But here, as the first takeaway, we can see that our attentive temporal pooling mechanism is obviously outperforming really simple baselines like average pooling and majority voting. But the more important takeaway is that the two-layer residual stacked affine transform that we propose as a classifier transfer method is the best option. So we have one layer, two-layer, and two-layer with residual connections, and we can see that we are able to push it to the limit with the two-layer RSA. And I would like to note down that we have tried with more layers, but we got diminishing returns, and we're not including that in our results. So as a second ablation study, I would like to, again, take a step back and remind you that in our problem, we have a fixed classifier that is trained on domain A, and we want that domain A classifier to work well with representations of domain B. But in our problem, we are not fine-tuning the classifier, and we are not fine-tuning the fixed image representations, right? But the question that we wanted to answer was, what if we fine-tune the classifier with violent videos? So this is more of a case where will the additional data, so our attentive temporal pooling mechanism or our RSA mechanism, will they be able to exploit more data in the other domain, in a transductive setting, let's say? And the answer is yes. They work well, and maybe we're not seeing a huge, like a dramatic increase compared to our alternatives, but compared to the previous results that I've shown, we get significant improvements. And what that means is that our mechanism can make use of additional data too. And finally, I would like to show the final results of our paper. And on the left-hand side, actually, right now we are including our more complex, more sophisticated temporal adaptation methods, as well as classifier transfer methods. And on the left-hand side, you can see the results without any classifier transfer. And on the right-hand side, you can see the results with classifier transfer. So on the left-hand side, you can actually see without classifier transfer, self-attention. And I would like to add a heavily tuned self-attention. And by heavily tuned self-attention, I mean we made sure that it works really well in our case. But anyway, self-attention works better than what we proposed in a no classifier transfer regime. And that actually does make sense in a way, because self-attention actually does a feature transformation in the multi-head attention mechanism, as for those of you who are familiar with it would know. So there's an inherent, like an implicit feature transformation happening in self-attention. So, but still, when compared to our ATP, even though our ATP is performing worse than self-attention, I would like to point out that our ATP has significantly less complexity than a self-attention mechanism. But in a case where we actually implement classifier transfer, we can see that ATP, our proposed method, significantly outperforms all the alternatives, even self-attention and another baseline method that specifically focuses on cases like ours. So to conclude my my presentation, before I conclude my presentation, I would like to show some qualitative results. And here in that slide, you can see 3 image sequences. And above each frame, you can see the attention scores assigned by our method. And as you can see, our method attends to images with less blur, and actually attends to images with distinct poses. So it is trying to make use of different viewpoints and different representations that we can learn. So long story short, it does what we want it to do. So that is basically the bulk of my presentation, and I would like to conclude by pointing out the potentially important parts of my presentation. So what we did is we formulated what we call partially supervised domain transfer problem, and which is based on common surveillance scenarios. And what we mean by that is that the problem has elements of limited data, extreme class imbalance, multiple domains and modalities. And second, to create a testbed for our problem, we curate and release WildestFaces dataset, which actually is comprised of clean image and violent video datasets. And as I've tried to mention earlier, we have annotations available for face recognition as well as face detection. Third, basically, we introduced new evaluation protocols for face recognition for our problem, which are inspired from recent advances in zero-shot learning. And fourth, having the new evaluation protocols in our data set, we introduce attentive temporal pooling and residual stacked affine layers as low-cost and accurate alternatives for our newly proposed problem. And we show that our approach, although it is significantly less complex, it shows improvements over both domain adaptation and temporal aggregation baselines. And lastly, and I think this is the most exciting one, there's still a huge room for improvement. And as you can see, as you probably saw in the previous slides, the best results we were able to get were around 40 or 45% accuracy. So there's still huge room for improvement, and hopefully this talk will somewhat inspire people to work on this problem and further improve our results. Thank you for listening, and thank you for having me, first of all. Again, as I said, this was a collaboration with several authors. And if you want to find more about our data set and our paper, you can visit the website shown in the slide. And hopefully you enjoyed it, and just feel free to ask any questions.
Thank you, Mehmet. It was a really nice presentation.
Thank you.
Any questions from the audience? Okay. Maybe I can start in the meantime. Did you you didn't need to do, I guess, face alignment or other pre-processing steps, right? That people usually do.
Actually, we do, but not extensively. I remember us using MTCNN for face alignment, but obviously individual face alignment approaches, they make assumptions, and especially in the presence of blur or occlusion, they don't really operate. But as a short answer, yes, we did, but because of the nature of the data, it actually doesn't do what it's supposed to do.
Okay. And if I were to approach this problem, probably I would have first tried disentangling the representations, for example, poles and other illumination, etc., and have just a representation for identity. But I guess attention is handling that for you, right? Is that a correct interpretation?
It is. So our interpretation, what we saw was that, as I tried to show, it handles blur. That's one of the most consistent trends that we saw. And it also tries to pick different poses. And by basically, in other words, it tries to avoid repetitive images unless they are really the only informative frames in the sequence. But as you've mentioned, disentangling the representations are the natural way forward to improve this problem. Because, and I think it is more exciting in our setting because our problem is operating in a limited data regime. So if we had millions of videos or images, that would maybe a network would implicitly learn it, but that's not going to be the case probably in our scenario.
Yeah, that's interesting. Any questions from the audience? Otherwise, we can stop recording and switch to a more informal session. Okay. Thank you, Mehmet, again. So let's stop recording and we can continue informally.